Ben, looking forward to the talk by Jian Zhang about specific attenuation-based radar QPE for operations.
Okay, hello everyone. My name is Jian Zhang. I'm from NSSL, same as Alexander. I will talk about a specific attenuation-based radar QPE for operations. And first, I would like to thank my colleagues, Drs. Lin Tan, Steve Cox, Pengfei Zhang, and Alexander, who are all the main contributors to this work. So a little bit of background. This work was motivated by the polarimetric upgrade of the US weather radar network. So in order to take advantage of the dual-pole upgrade, we want to improve the operational radar QPE using the dual-pole variables. We evaluated several dual-pole radar QPE techniques, and based on the evaluations, we found that specific attenuation-based QPE seemed to perform the best. So we developed a specific attenuation QPE, and we implemented that in a real-time system we called multi-radar, multi-sensor, or MRMS, if you have heard of it. We implemented in a pseudo-operational environment and applied to all radars in the US. Then extensive evaluation and refinements followed. Then the technique become mature enough. Now it is transitioning into operations. Actually, right now, it will be online operationally the 14th of this month. So this talk presents some of the advantages and the challenges that we found through all our evaluations and testing. I'm glad Alexander already talked about the detail of the RA methodology. So I won't go through all the equations. And this on the right-hand side is the plot for estimating the key parameter in the RA algorithm, which is alpha. So this is a function of the ZDR slope we call K, and K is showed here. It's a linear fit to these black dots, which are median ZDRs for each given 2 dBz reflectivity. These data samples are collected from the lowest tilt of the radar, which is 0.5 degree in the US. Then once we have the slope of this linear fit, then we can estimate alpha. And we kind of threshold them at the top to 0.04, and at the bottom is 0.015. I would like to point out two key advantages of RA scheme. Is one, if you look at these equations, you'll notice that reflectivity appears in both the denominator and the denominator, because A is in I and also in this. So this kind of effectively removed the dependency of the systematic biases of Z. So this made the RA scheme is less sensitive to systematic biases in the reflectivity, including partial blockage, attenuation, or wet dome effects. Also, since alpha is a function of the slope, it is also insensitive to the systematic biases in the Z and the ZDR. So we'll show some examples of this kind of advantage later in examples. So since RA is only applicable in the pure liquid phase, so how is this applied in operations? Because we observe all phases of precipitation. So this is a kind of a flow chart of how RA is merged into the operations. So below the melting layer, we calculate RA and RKDP. Then we mosaic this RA, RKDP to the CONUS, the continental US domain. RKDP is applied in areas that we think hail is potentially exist. So basically, if Z is greater than 50 dBz, it's all RKDP. If Z is below 45 dBz, it's all RA. And in between, we have a kind of a transition zone, a linear combination of RA and RKDP. So this mosaic will have holes beyond the melting layer because we don't have data RA beyond the melting layer. Then we have a multiple RZ algorithm that's applied everywhere across CONUS. This RZ apply multiple RZs based on an automated precipitation classification and has a VPR correction to mitigate the bright band contamination and to mitigate potential underestimation associated with the radar beam overshooting or partially overshooting precipitation at the far ranges. So below list some of the RZ relationships that was used. So the plot in the lower right shows how this work kind of visually. You see the dark blue is areas above the melting layer. So it's all RZ applied. Then the green area is where RA was applied 100%. Then the yellow area is a 50-kilometer transition zone from RA to RZ. We have a linear transition to avoid the sharp boundaries. Then you will see some red and orange pixels in this plot. That's where RKDP was applied. So this is how RA is merged in the operational QPE, so we can apply everywhere across CONUS. So like I said, we've done extensive evaluations of this synthetic QPE. So this slide shows a 1-year categorical hit-miss plots. So basically, there are two parts. The top part is our old multiple RZ-based QPE. The bottom is RA-based synthetic QPE. So the diagonal line shows where the gauge observed and the radar QPE match in the same category. If you can see my cursor, I'm not sure if you can, but the diagonal highlighted color values are the hit values. And how the category is defined is listed below from very light to extreme precipitation. So the key point here is the RA-based QPE has a much better hit rate for the moderate to very heavy rain, especially for the extreme rain, which makes sense because that's where the attenuation signal is the best. Then you'll see there is this light category where the RA-based QPE didn't perform as well as the old multiple RZ QPE. And I will explain why later, show some examples. So this is the, I think, a key advantage of RA is it provides better estimation for heavy or very heavy rainfall, which is very important for our flash flood and flood predictions. So next, I'll show some specific event examples to help us understand where it performs well and where it still have challenges. So you'll see some images and some statistics, which I listed here. The first is a bias ratio. So if it's greater than 1, the radar QPE is overestimating. If it's lower than 1, it's underestimating. Now we have correlation coefficients and mean absolute error to show the random error. Okay, so first case to demonstrate RA advantage in heavy warm rain. So you can this slide, the following slides will show the same plot. This is the top row is our old multiple RZ based QPE, and then bottom row is the new RA based synthetic QPE. These are 24-hour accumulations compared with the manual gauges. It's the US CocoRAS gauge network. Now here are the statistics I mentioned. Red means worse, blue means better. Here is the, I mentioned the automated precipitation classification, which has several categories. You can see the 2 greens are the tropical rain, dark green tropical convective, light tropical stratiform. Then the purple is hail. The cyan is the cool stratiform, and the dark blue is a warm stratiform. Then red is convective. So you can see for this case, it's mostly warm rain, some convective warm rain embedded. Then below you have some little pockets of convection and hail. And the lower right, you can see the reflectivity and the ZDR plots. The black circle shows the bottom of the melting layer. So within the black circle is where RA was applied, and that's the center of the radar. Then the most lower right is the ZZDR plot to show the slope and the alpha value. So in this case, you can see the ZDR value are small, reflectivity is moderate, and the ZDR plot is very flat. So that's why alpha was very high, indicating kind of warm rain, heavy precipitation rate type. In this case, in our RZ, because warm rain was identified, there was actually an enhancement multiplier, which is 1.25 times the tropical RZ. So there was a enhancement applied, but still RZ was underestimating, as you can see from the stats. So this shows how RA is better related to the liquid water content in the precipitation system. So this case is a convective rain case, similar plots as you can see. Now you can see we have in the lower right, the ZDR scatter plots. You can see we have some higher ZDR associated with the high Z. So you see a upwards slope. And so the alpha value was lower, indicating a convective type drop size distribution. And you see the RA again captured the precipitation well and had a better statistics. Next case is a hurricane case, as you can see from the precipitation type plots and the reflectivity. Again, you see the ZDR scatter plot in the lower right, very flat slope and high alpha values. And the one key feature I would like to point out is the partial blockage in the to the southwest of the radar due to trees. So it had a big impact on the RZ-based QPE, but had little impact on the RA. And also, again, this RZ QPE had like a 1.5 factor applied on tropical RZ. Did pretty well in some areas, but probably in partial blockage areas still had a lower underestimation. And the RA showed a much better performance in this case. So next case. So this is a severe blockage case. you can see here is the blockage in the 0.5 degree of this radar. So in this case, we had like a quite low reflectivity. You can see from the lower right ZZDR scatter plots, there was little reflectivity above 40 dBz. So all the reflectivity were below. In this case, we didn't apply a slope. We simply identified this case as a pure stratiform event, and we applied a predefined default alpha 0.035 for this case. So in this case, RA performed better in terms of bias and mean absolute error, but had some slightly lower correlation coefficients. So next case is a very light stratiform rain. Remember, we just talked about when the reflectivity is very, very low, we applied a default alpha 0.035. But for this case, we actually had underestimation compared to the RZ based QPE. So we've seen a lot of similar cases. So we went back, looked at the alpha value that we used. Then we found, if you look at the upper right plot, this was based on drop size distribution data derived by Richkoff et al. 2014. So initially, this value was chosen for stratiform. We kind of picked a median across all the ZDR. But if you look at this scatter plot, you can see when the drop size becomes smaller, the ZDRs become smaller, the alpha actually increase quite a lot. So 0.035 is probably not representing of this drop size distribution in this type of precipitation, and the value may be too low. So we are developing refinements to the RA to address this, and I'll mention later. This is a case that RA didn't perform well, which is a widespread stratiform and a strong convection mixed case. So you can see in the three panels with the black, big black circle. So this is where our ZZDR sample were taken. So you can see that since they are so large area of stratiform, the ZZDR plot, scatter plots in the lower right, was quite dominated by the large area of stratiform rain. So you can see the alpha is kind of in the moderately high category, 0.0266. So this alpha is applied for the whole domain. That's the current approach, and resulted in overestimation in this leading convective band. And you can see in the left, the bubble chart shows the where the gauges are, and the color shows the ratio of the gauge over radar QPE. So here, if you look at the color bar in the blue area, is where gauge is much lower than radar QPE, meaning radar QPE was overestimating. In this case, if we look at the statistics, it's about 20% overestimation. So this is also a recurring situation we've observed. So we think this is the issue associated with apply a mean alpha across all domain, the whole domain, even though the alpha was updated every volume scan. So like in this area, the high ZDR area, if we look at the upper right plot, the alpha, if we look at if for ZDR greater than 1 dBz, the alpha is mostly below 0.02 actually. So 0.0266 is too high for this convective area. So we'll talk about how to address this in a few slides. Oh, actually, right at this slide. So this is a refinement of RA. We are trying to address the issue I just mentioned. So we were based on the alpha-Z relationship derived from the drop size distribution data. This was also from Alexander. This was separated for kind of a marine time, relatively small drops, many of the drops, and relatively continental. So to address the highly non-uniform DSD distribution, we developed a kind of empirical bulk adjustment to the RA that we've derived. You can see this red part in the formula. We have an alpha adjustment over alpha naught. So alpha naught is what we are using now, and we apply a alpha adjustment here. And this adjustment curve is shown in this scatter plot in the lower left. So we experimented two curves. One is for marine time. You can see this green line in the lower left panel. It's a function of reflectivity. So if the reflectivity is higher, then the alpha adjustment is lower. And if its reflectivity is lower, the alpha adjustment is higher. And this slope is higher for marine time rain because it has a higher precipitation efficiency than the continental rain. So you can see these two curves. So on the right, I kind of showed three specific examples when these adjustment curve will be applied. So on the top row is the pure stratiform case. As I mentioned, we underestimate. So for this case, we'll apply the marine time alpha adjustment everywhere across domain. In the middle row is for the stratiform convective case, where we had overestimation. We'll apply this marine time curve for reflectivity greater than 45 dBz. We are still experimenting this. We may lower 45 to 42 dBz. So we apply this because when this alpha naught is high, in general, the stratiform area actually is still pretty warm, kind of a warm rain type precipitation and has high precipitation efficiency. So the lower row, the bottom row, is a weak convection, where you also see there is not much higher reflectivity above 40 to 45 dBz. The current scheme also identified this as stratiform and applied a high alpha, which caused overestimation also. So for this case, we will apply a continental alpha adjustment, and we are still refining this. So some initial results from this adjustment. The three panels shows the RZ-based QPE. This is for mixed stratiform convective precipitation regimes. We have 77 events in here. So the left is RZ, middle is RA, the current operational RA. Then the lower right is our new adjusted RA. So with the adjustment, the most significant improvement is the reduce of the scatter. So we reduced some of the overestimation in the mixed rain. So the random error and the correlation are all improved. So is the bias. Then this shows the pure stratiform As I mentioned, we had a low underestimation in RA. If we look at the middle panel, you see obvious systematic biases in these plots because that's where the RA signal was relatively weak, also because our alpha was not representative of the precipitation drop size distribution. So with the new adjustment, we significantly improved the bias and also the random errors. So in summary, so I kind of introduced our specific attenuation-based S-band radar QPE, which is in transition into operations. I showed some examples to demonstrate its advantages. So the most significant is it has lower bias and random errors in warm season heavy rain, regardless of precipitation regimes, which is very important implication for operations. It's insensitive to partial blockage, insensitive to systematic errors in ZZDR, and also for like a small number of ZDR, bad ZDR values like associated with the trees, the RA is insensitive because we based on the median ZDR and the ZDR slope. So it makes RA a little bit more robust and less sensitive to those bad ZDR data. The challenges, RA is only applicable in liquid phase. So we still need to face challenges with the frozen phase. So we noticed a dry bias in light stratiform rain due to an unrepresentative of alpha. We also had noticed overestimation, sometimes actually underestimation in mixed rain because we are using a domain average alpha and under highly non-uniform DSD distributions. So we are developing a Z-based RA adjustment to address this highly non-uniform DSD distribution, and we see some very promising results. And we are continuing refining and hoping to transition that into operations in the next year or so. So with that, I thank you for your attention, and I can take questions.
Thank you very much, Jan, for this nice, interesting talk. You said your algorithms are now into transition to operations, but this MRMS product is now also generated in a routine basis, but based on earlier algorithms. We heard also in the morning by Dave Turner that he's also using it, for example. So there is a standard product available every day?
Yes, we have two MRMS systems. One is the truly operational MRMS that's running at the Weather Service headquarters, actually NCEP. So that's the operational system. As of today, it's still running the multiple RZ. That's the operational QPE. But in a couple of weeks, the new dual RA synthetic QPE will become operational in that system. Then there is a research system also running 24/7, but at NSSL. In that system, we can tweak the algorithms, do a lot of experiments. So that research system always running algorithms newer than the operational system. But a lot of users also are willing to test our research products from NSSL system.
Oh, yeah, we here in Germany heard already a lot of good things about your product, so I'm eager to see it once. Thank you very much.